Welcome to Introduction to Building Codes, Bangladesh National Building Code 2020, referred to as BNBC 2020. Part 8 Building Services, Chapter 1 Electrical and Electronic Engineering Services for Buildings, Part 1 Electrical Presentation. The description of this presentation is designed to familiarize and assist code officials in locating, describing, and applying the applicable code requirements for electrical and electronic engineering services for buildings. This presentation also provides owners, engineers, inspectors information for the same type of systems regarding electrical and electronic engineering services for buildings. We will discuss specific topics related to lighting, power, and the utilization of electrical equipment and appliances. Our overview of the course contains the following information. Internationally, code officials recognize the need for a modern, up-to-date electrical code that addresses the design and installation of electrical and electronic systems through requirements emphasizing performance. This presentation will cover key topics of the following areas. We will discuss scope, which is the intended use of this particular code, whether you are supposed to be in the code with respect to the application or proposed electrical system. The terminology and definitions are important due to the fact that classification and proper terminology of our electrical and electronic systems is essential for participants to understand to utilize this particular code. We will also discuss lighting and illumination. Lighting and illumination values are given in the code as to provide a minimum illumination level for different areas within our buildings. Finally, electrical and electronic installations within buildings will be covered as well. Our seminar goal is as follows. The goal of this training is for you to learn and apply key code requirements contained in Chapter 1, titled Electrical and Electronic Engineering Services for Buildings, to enhance your performance while inspecting these systems. Additionally, if you design the systems, if you are an owner of a building, this course will be invaluable to you in providing key information as well for electrical and electronic engineering services for your particular buildings. This training will also provide participants with specific code requirements, with examples related to design, installation, and inspection of electrical and electronic systems to further enhance your knowledge. Upon completion of this course, the main objective here is for participants to be better able to locate general topics located within Chapter 1 regarding electrical and electronic engineering services for buildings, locate applicable codes and standards for specific situations, apply code requirements to real-world situations, explain the intent behind a given code requirement, and finally, to use good judgment to identify certain systems and related components as compliant or non-compliant. Chapter 1, Section 1.1, titled Introduction. This particular section, 1.1.1, Scope, indicates the provisions for the code requirements. The provisions of the code presented in this chapter cover the electrical and electronic engineering services for buildings to ensure that the related installation work becomes perfect and safe for the persons residing in and around the building. The term safe means safe for the person and safe for the properties. Given this part of the code, it mandates that we have to have a very safe installation to protect the lives of the people within the buildings that we live and work in throughout Bangladesh. Provisions of these specifications are to set minimum standards for electrical and electronic engineering installations, such as various occupancy categories of buildings, as described in Part 3 of this code, including annexes and premises. All the system and equipment intended for supply of normal and standby power to all these places are covered by the provisions of this code. An electrical and electronic code cannot be effective without adequate provisions for its administration and enforcement. This paragraph lays out the importance of a good code program and proper inspection of these electrical systems. Section 1.1.1 Scope continued. There are several hazards associated with electrical systems, including but not limited to shock and burns from contact and building fires from faulty wiring. A properly designed system with a code-compliant installation that is ultimately reviewed, inspected, and approved by properly trained code officials is vital in ensuring electrical systems are safe for people and buildings. The code official is charged with the administration and enforcement of electrical regulations, and also has a great responsibility to do so and carry out the duties to make sure that people are safe after the installation of electrical systems. This responsibility drives his or her authority accordingly. Additionally, the provisions of this code for various electrical and electronic engineering systems and/or installations for the buildings include, but are not limited to, the following: lighting and illumination. Lighting and illumination indicated in item A is necessary such that we can function within the building under proper lighting or illumination levels for working, living, eating, cooking, sanitation purposes. Item B, fans, cooling, and heating. These are environmental conditions within the building to keep us comfortable as we live and work in our buildings around Bangladesh. Item C, normal and standby power supplies. Certain occupancies will have standby power supplies as to fortify the necessary need for electrical power within certain buildings. Item D, supply system and feeder for lifts, escalator, moving walk, including protection. Item E gives us cable television distribution. Item F, electronic access control. The scope is also continued in item G regarding burglar alarm, CCTV monitoring, security systems. Item H, electrical cables, conductors, and equipment. Item I, switches, sockets, and other accessories. Item J, cables and conductors in a building that connect the supply of electricity. Item K, electrical protection system. And last, item L, earthing system of an electrical installation. Continuing from the list, item M, lightning protection of a building and its electrical installation. Additionally, we have fire alarm requirements, as the scope indicates, within many buildings that are required to be provided with a fire alarm. Finally, item O, multimedia communications, data communications, and telecommunications. In order to effectively administer the code, a code official must clearly understand to what extent the code applies. As the code official applies a given code provision, the intent is to make sure that the application fits the scope of the code. That is the language that is so necessary in the scope part of the code. The scope, while not entirely complete, does provide a level of clarity as to the work and activities that fall under the provisions of this code. The provisions of this code in this chapter do not cover installations in ship, watercraft, railway, rolling stock, aircraft or automotive vehicles, and recreational vehicles. Continuing with the scope requirements, electrical wiring, cabling form a major part of the previously mentioned installation works. Electrical wiring and cable must be reasonably safe to person and property. Installations, alterations, extension of electrical wiring and cable systems conforming to the provisions of this code shall be deemed to be reasonably safe to persons and property. If designed and installed in compliance with the applicable portion of this code, an electrical wiring and cabling system is considered safe for people and property. In other words, building, and by administration and guidance of this code, the installation is reasonably safe for the people that occupy our buildings. The code establishes the minimum thresholds for electrical systems to operate safely. Section 1.1.2, Designing an Electrical and Electronic Engineering Installations in Buildings and Related Structures. The provisions of the code presented in this section are not meant to provide adequate information to design electrical and electronic engineering installations and systems in buildings and related structures. These should not be taken to be adequate or complete for the efficient design work of installations. Such design work, the required features, detailed technical specifications, schedule of items, etc., should be obtained through the services of an engineer adequately qualified in this area. Applications of energy-efficient appliances should be kept in mind while preparing electrical design of a building or related installations. The code clarifies here that the code is not meant to be taken or utilized as a design manual to perform complete electrical system designs. It is very clear here. This type of work should be reserved for a qualified engineer, which will use other design references, equations, standards, etc., to complete the electrical design of the proposed building or system within the building as to function properly and safely. Section 1.1.3, Terminology and definitions. This section provides an alphabetical list of the terms used in and applicable in this chapter of the code. In case of any conflict or contradiction between a definition given in this section and that in Part 1, the meaning provided in this section shall govern for interpretation of the provisions of this chapter. A code provision could be misinterpreted if the definition of a term as used in the context of the code is not understood. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes, by their very nature, are technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understanding the provisions of this code. Definitions are found both in this chapter and throughout the code. Let's take a look at some key terminology relating to electrical and electronic engineering installations. The term BDB is defined as Branch Distribution Board. The branch distribution board located in the same floor of a building and connected to one of the SDBs in the same floor. Circuit breaker is defined as a device designed to open and close a circuit by non-automatic means, and to open the circuit automatically on a predetermined overcurrent without injury to itself when properly applied within its rating. Circuit breakers are used for protection of our conductors that supply electrical power to equipment and appliances utilized within our buildings. The term DB, distribution board. This may be the box where the main incoming cable enters and terminates from the main service feed connection. The SDBs get fed from a DB, which is a distribution board. As can be seen in the photo below, the conductors that come up from the bottom in the middle of the picture are terminated on a circuit breaker accordingly in this distribution board. From that point, the branch circuits and feeders are distributed accordingly to their respected loads. The term Earth is the conductive mass of the Earth, whose electric potential at any point is conventionally taken as 0. Earth continuity conductor, abbreviated as ECC, is the conductor including any clamp connecting to the earthing lead or to each other, those parts of an installation which are required to be earthed. It may be in whole or in part the metal conduit or the metal sheath or armor of the cables, or the special continuity conductor of a cable or flexible cord incorporating such a conductor. ECCs of appropriate size must run from a MDB to its DB, which are distribution boards, from a DB to its corresponding SDBs, and from an SDB to the switchboards under this SDB, from an SDB to the DBDs, if there are any, From a branch distribution board to the switchboards under this DBD, from an SDB or a BDB to the sockets under this SDB or BDB. This definition makes it clear the function and the routing of the earth continuity conductor. We will have many examples of this application coming up in this presentation and also in the electrical part 2 presentation as well. The term live is described as electrically charged so as to have a potential difference from that of Earth. It's also known as alive. MDB, main distribution board. This is the distribution box where the main incoming cable enters and terminates from the main service feed connection of a large building. The FDBs get fed from MDB. SDB is defined as sub-distribution board, located in the same floor of a building and connected to the DB, which is the distribution board, as previously defined. The BDBs get fed from the SDB. Recall the definition BDB, branch distribution board, that is located in the same floor of a building and connected to one of the sub-distribution boards in the same floor. Below is a description indicating the sub-distribution board that feeds a branch distribution board. As can be seen, we have a live conductor, a neutral conductor, and an earth continuity conductor that is sized properly for the load of the branch distribution board. Section 1.1.4 Voltage Ratings. The provisions of the code specified in this chapter cover installations utilizing nominal voltage not exceeding 415 volts AC between conductors, or 240 volts AC to earth. The nominal voltage in Bangladesh is 230 volts AC single phase and 400 volts AC three-phase. Indicated below is a 230 volt AC single-phase system. This is located on the secondary winding of the transformer. The primary side will be a higher voltage, which is then reduced to a single-phase 230 volt alternating current system, as can be seen here in the graphic. We have a live phase and a neutral that is brought to the building for service regarding this single phase system. An example indicated in the diagram below indicates a 400 volt AC three-phase system. The four-wire system includes 3 live wires or 3 phases and a neutral wire. The voltage measured between any of the phases is 415 volts. As we can see in the diagram below, if we take a voltage measurement between phase 1 and phase 3, the resulting difference in potential is 415 volts. From phase 1 to phase 2, 415 volts. From phase 2 to phase 3, the resulting voltage again is 415 volts. The voltage measured between any of the phases in the neutral wire is 240 volts. As can be seen in the diagram, if we take a measurement between phase 1 and the neutral wire, the resulting difference is 240 volts. From phase 2 to the system neutral, again, 240 volts. And finally, from phase 3 to the neutral wire, again, provides a difference in potential of 240 volts. This type of system, this three-phase 400-volt system, would be utilized more frequently in commercial buildings that utilize larger equipment and larger motor loads. Section 1.2, Lighting and Illumination. Determination of illumination levels for different application. The design of a lighting system shall involve the following. As itemized here, we need to understand that there is careful planning of the brightness and color pattern within both the working areas and surroundings so that attention is drawn naturally to the important area, so that details can be seen quickly and accurately, and so that the appearance inside the room is free from any sense monotony. Item B, use of directional lighting to assist perception of a task detail. Controlling direct and reflected glare from light sources to eliminate visual discomfort is given in item C. Another item, minimizing flicker from certain types of lamps and paying attention to the color rendering properties of the light, is important as well for user comfort and distraction characteristics. Item E, the correlation of lighting throughout the building to prevent excessive difference between adjacent areas so as to reduce the risk of accidents. And item F, the installation of emergency lighting systems whenever necessary. Emergency lighting systems are necessary for proper egress out of the buildings upon a power loss within the building. A well-designed lighting system can make a significant difference in the look, feel, and quality of work that can be completed in a building. Consider different applications and the need for different types of lighting. The necessary lighting system in a factory, perhaps where small components are hand assembled, is significantly different than the desired lighting system in a museum where colors and lighting effects would be important. In either case, we need to understand the application for the design of the lighting system and the different illumination levels as well as the color correlation of lighting within the space. Section 1.2.1, Determination of illumination levels for different applications, continued. The general impressions associated with different illuminance and color appearances of light are shown in Table 8.1.1. The various color rendering groups with examples of use are presented in Table 8.1.2. As we look at Table 8.1.1, titled General Impressions Associated with Different Illuminance and Color Appearances, the first column gives us the illuminance in lux. Values less than or equal to 500 we have the range of 500 to 1000 lux, 1000 to 2000, 2000 to 3000, and greater than or equal to 3000. The associated impression, which is the color appearance, is given in 3 separate columns: the warm column, the intermediate column, and the cool column. The general impressions help us understand how the lighting affects us personally. So here again, on the far left side, we have the level of illuminance measured in lux. We need to understand that the lux is the intensity of the illumination of an area. Think of it as a flashlight shining on a table. As the flashlight gets closer to the table, the illumination intensity on that table will increase. As we move the flashlight away from the table, the illumination intensity will decrease. To give some equivalencies or examples for the number of lux, consider a full moon on a clear night having a lux of 1. 100 lux may be very dark, overcast day. 400 lux may be sunrise or sunset on a clear day. Overcast daylight may be determined or compared to 1000 lux. Direct sunlight would be a value of 32,000 lux, just to give you a perspective of what the illuminance is referring to. Therefore, the next set of columns we have again are the color appearance, which are warm, intermediate, and cool. Warm colors, reds and oranges. We have intermediate colors that are yellow, greens, transitioning to warm and cool, and cool colors, greens, blues, and violets. So the color appearance columns provide the impression at various illumination or illuminance levels. Color appearance can be driven by the lamps themselves, as different types of lamps will emit a different color appearance, and the color of the surfaces the light is shining onto, or a combination or both. As you can see from the table, in the warm color appearance column, warm colors would not have a pleasant or neutral appearance at higher levels of illuminance. As we can see by applying the table, if we have an illuminance level in the range of 2000 to 3000, and we enter the warm column, this is a stimulating to unnatural type of lighting as it is impressed upon us. If we look at the same range of illuminance between 2000 and 3000 lux, and we go to the cool column, this impression on us is neutral to pleasant, as you can see at this higher illuminance level. As we go down in illuminance, maybe the range of 500 to 1000 flux, and we enter the column of warm. This is pleasant to stimulating. When we enter the intermediate column for the same range, 500 to 1000 lux, it tends to be neutral to pleasant. When we enter the very last column of the range indicated as 500 to 1000 lux in the cool column, the color appearance associated with our impression tends to be cool to neutral. As an example, notice the differences and effects under different kinds of lighting. The kind of lighting can provide a dramatic effect. This picture, the same person under different kinds of light is indicated. Notice the shape of the nose based on the shadows between the two pictures. The crispness and color in the eye surrounding the pupil in the top of the picture versus the bottom. The obviousness of the bottom eyelashes in the bottom picture versus the top. Each type of lighting can be used for desired effects. And we can clearly see the warm differences on the bottom versus the more bright or cool aspects of the top picture. So given the color and the illumination levels, we can see a dramatic effect on how lighting affects the way we see things in detail with respect to people, finishes in buildings, and overall sight. Table 8.1.2, Lamp Color Rendering Groups. This table represents recommended color rendering group based on building use and color appearance. The first column is the color rendering group. This is just to group the color rendering index ranges. You may ask, what is color rendering index range? And what does it really mean or measure? The color rendering index defines the ability of light source, which is a lamp, in this case, to identify colors. It is measured on a scale of 1 to 100. 100 is natural sunlight, and 1 is light of a single color, monochromatic. A higher rendering index, colors will appear much clearer and move more vibrant. The next two columns provide the color appearance, where lamps of the various color rendering index should be utilized. Halogen and incandescent bulbs have an index of around 100, while LEDs are around 80, depending on temperature of the bulb. As we can see, the range of index R sub A with respect to the color rendering group is given to us. Color rendering group 1 gives us a range of index R sub A greater than or equal to 85. Color rendering group number 2 gives us a range between 70 and 85. And coloring rendering group 3 gives us a range of between 40 and 70. The color appearance, as seen in the third column, in color rendering group 1, cool, intermediate, and warm. The examples of use are given in the last column. For a cool color appearance in color rendering group 1, this is for textile industries, paint and printing industries. The intermediate color appearance for shops and hospitals would be good examples of their use. And a warm color appearance, such as homes, hotels, and restaurants, would fit color rendering group 1 in the warm color appearance. Offices, schools, department stores, fine industrial work have a range of index between 70 and 85 in color rendering group 2. The color appearance would be intermediate for these type of occupancies. And finally, interiors where color rendering is of comparatively minor importance gives us color rendering group 3 and the range between 40 and 70 as the index. Section 1.2.3, titled Lighting Calculations. In order to determine the necessary number of lamps and luminaires for a specific illumination level or the average illuminance obtained from a particular lighting design, the Lumen method of calculation shall be employed. The lumen is a unit of luminous flux that is a measure of the total quantity of visible light emitted by a source per unit time. The unit that we use and the formula provides us with the average illumination. The Lumen method formula is E equals F over A, where E is the average or minimum illumination level at the work plane in lux. F is the useful lumen output of all sources in lumens. A is the total surface area of the working plane in meters squared. Lighting calculations continued. Note that the value F is useful lumens and not lamp lumens. Several factors can affect a light's ability to reach the working plane and include the following: the distance of the light fixture from the working surface, the proportion and size of the room, the reflectivity of the ceiling, wall, and working plane surfaces, particulates in the air that may diffuse the light, type of a fixture, and the way it distributes light, loss of lighting due to aging fixtures, lamps, and dust. As you can see, there's many factors that go into the value F based on the list of these variables. Factors such as these must be taken into account for proper lighting system design. Section 1.2.3.2, continuing our discussion on lighting calculations, indicates the requirement, unless the reflection factors are known to the lighting designer, the triplet 0.7, 0.5, 0.3 for the reflectance of ceiling, walls, and working plane, respectively, shall be used for offices, and the triplet 0.7, 0.5, and 0.1 for other premises. Typical reflection factors of smooth colored surfaces are given in Table 8.1.4. Unless we understand the reflection or the reflection factors, we need to look at the table and figure that the color and the reflection factor has a bearing on the lighting design. As we can see, reflection factors of smooth colored surfaces such as flat white has a reflection factor of 0.75 to 0.85. When we get into the darker colors at the end of the third column, such as dark brown, we have a reflection factor of 0.10 to 0.15. As you can see, we have got a wide range of reflection factors to choose from with respect to the colors that are being placed in rooms, such as ceilings, walls, and working planes. Recommended illumination values are given in section 1.2.4. The recommended values of illumination required for buildings of different occupancies based on activity are given in tables 8.1.5 to 8.1.14. The initial illuminance should be higher than the recommended value, as the illuminance drops below this value by the end of the cleaning and replacing period. A gradual transition rather than a sudden change of brightness from one portion to another, within the field of vision is recommended to avoid or minimize glare, discomfort. It should be noted that per section 1.2.2.1, the minimum illumination of working areas within a building is 150 lux. Table 8.1.5 to 8.1.14 provide recommended values for illumination in the various portions of a building. As seen here, Table 8.1.5 titled Recommended Values of Illumination for Residential Buildings. The area or activity is indicated in the first column with the category dwelling houses. To the right of the activity indicates the illuminance in lux. For bedrooms, general areas within the bedrooms, we need to have a minimum lux of 70. Kitchens, it goes up to 200 lux. Dining rooms, 150. In bathrooms, the general lighting area would be 100 lux. When you have detailed work such as shaving and makeup, the illuminance goes up to 300 lux. Stairs, as you can see, is 100. We move down the list to sewing and darning. That would be 600 lux. We can see the more detailed work that we have within our dwellings, we have to have more lighting. Homework and sustained reading is 300 lux. When we look to the right side, second half of the table, the category is hotels. Entrance halls have a minimum illuminance of 150. Reception and accounts, 300. This is where we have detailed paperwork and reading at the reception and account area within hotels. As you can see, the illuminance levels go up for this task type work in our hotels. We have writing rooms, tables at 300, and going further down, above mirror in bathrooms also has a minimum illuminance of 300. The level of illumination is directly related to the use of the building and the use of the space within that building. However, notice that the required level of illumination can be highly variable in a building. Table 8.1.6, titled Recommended Values of Illuminance for Educational Buildings. The area or activity is indicated in the first column, as was the previous table, with the second column giving us the illuminance in lux. The category school and college assembly halls contains general areas when used for examination areas and platforms with the associated lux value for illumination. When we get into the art rooms of these areas, it goes up to 400 lux. As you can see, we need more and more illumination. Across the table, we have offices at 300 lux, corridors, stairs, gymnasium areas, general areas, 100 lux. We have table 8.1.7 below. Recommended values of illumination for healthcare buildings. Hospital and clinic, this category. When we have areas such as reception and waiting rooms, we have a minimum value of 150 lux. Operating theaters vary based on general 300 lux. Tables with adjustable operating lamp lighting, we have minor and major. The minor is a minimum of 2000 lux with a major adjustable operating lamp of 5000 lux. Adjacent to the right, hospitals and clinics continued. We have different areas such as doctors' examination rooms at 150, radiology 100, and last but not least, dispensaries at 250 lux. As you can see, depending on where you are at within the building and the function of the building, the lighting level in illuminance or lux is a variable. Exit signs are covered in section 1.2.7.1. All required exit signs shall be illuminated at night or during dark periods within that area served. Exit signs may be illuminated either by lamps external to the sign or by lamps contained within the sign. The source of illumination shall provide not less than 50 lux at the illuminated surface with a contrast of not less than 0.5. Approved self-luminous signs which provide evenly illuminated letters having a minimum illuminance of 0.2 candela per meter square may also be used. Exit signs are important such that the occupants of the building can see the way to the exit and get out of the building safely in the event of power outages and dark conditions within the building. Exit signs continued. Item C, the illumination of exit signs and the lighting of the means of escape and exit access shall be powered by an alternate or emergency electrical system to ensure continued illumination for a duration of not less than 30 minutes. Pictured on the right-hand side is a self-luminous type exit sign which works by utilizing tritium or photoluminescence. Tritium gas, which is radioactive, is placed in a phosphor-coated tube which emits the light. In photoluminescence, a pigment that is capable and able to absorb and emit light photons is in the film that is placed over the sign. Energy from surrounding light sources is constantly absorbed until light is not longer supplied, at which the point the pigment emits a low level of energy light. The picture on the left-hand side is a powered, illuminated exit light that needs building power. On this type of light that requires building power, there is an accessory that can be purchased that has a battery backup in these exit light fixtures. Most of these come with 30-minute, 60-minute, 90-minute duration. The means of escape lighting is in section 1.2.7.2. The requirements take us to the meaning such that the means of escape and exit access in buildings require more than one exit shall be equipped with artificial lighting. The lighting facilities so installed shall provide the required level of illumination continuously during the period when the use of the building requires the exits to be available. All portions of the means of escape and exit access of a space must be illuminated by artificial lighting when that space is occupied, so that the path of exit travel are always visible and available for evacuation of the occupants during emergencies. The intent is to allow portions of a building to have the lights turned off when that portion is unoccupied. Means of escape, lighting continued. Item B, the intensity of illumination at floor level by means of escape lighting shall not be less than 10 lux, except that the minimum required floor level illumination of aisles in assembly halls, theaters, and cinema during projection of motion or still pictures by directed light shall not be less than 2 lux. 10 lux is approximately the same lighting level as found outdoors at twilight. It has been found that even this relatively low level of lighting renders enough visibility for occupants to evacuate a building safely. It is important to note that this lighting level is measured at the floor in order to make the floor surface visible. Levels of illumination above the floor may be higher or lower, thus allowing lights along steps to be used rather than general area lighting. The illumination of exit signs and the lighting of the means of escape and exit access shall be powered by an alternate or emergency electrical system as indicated. With respect to the graphic below, we have a graphic explaining the wiring for this escape lighting. Normal egress, illumination by premises electrical supply. As indicated, wiring of the lights in the corridor what appears to be an office space. We have the two-head emergency light affixed to the wall within the corridor. We have an automatic illumination in the event of failure by means of an emergency electrical system. Whether it's storage batteries, on-site generator, or the batteries located within the unit. And we properly call these unit equipment when each unit has its own battery supply. And the duration of the illumination after failure of the primary power supply must be not less than 30 minutes. Section 1.2.8, Selection of appropriate type of lamp. It is important to understand appropriate types of lamps for each purpose. The lamps which are used for purpose areas are as follows. General service lamps, incandescent lamps. General service lamps are well known. Incandescent lamps. These are available in a number of wattage ratings. However, most commonly used ratings are 40 watt, 60 watt, 100 watt, 150 watt, and 200 watt rated lamps are also used for special applications. These type of lamps produce heat and should be minimized while selecting for a particular design because other better choices are available. These type of bulbs contain a filament inside the bulb that is heated via electric power until it glows. The purpose of the bulb is to encapsulate the filament to protect it from oxygen as it would oxidize. Continuing with our section 1.2.8, fluorescent lamps. A fluorescent lamp uses electrical current to excite a mercury vapor inside the tube. This produces ultraviolet light inside the tube, which then causes a phosphor coating on the inside of the lamp to glow. Unlike incandescent lamps, these lamps require a ballast to regulate the current through the lamp. These fluorescent lamps are available in 20 watt and 40 watt ratings. These lamps are strongly recommended for reading room, education buildings, laboratories, office room, commercial space applications, factory illumination, illumination of areas around industrial plants and machineries, exterior lighting applications. 40 watts should be used whenever possible because a 40-watt fluorescent is more energy efficient compared to a 20-watt fluorescent. These are long-life lamps that have wide applications and are advantageous in many respects. Continuing with section 1.2.8, compact fluorescent lamp. These energy-saving lamps work the same way as fluorescent tubes. However, they contain a different type of compact ballast at the base, which allows them to fit right into light fixtures designed for incandescent lamps. The compact fluorescent lamps are available in a number of wattage ratings, such as 4 watts, 7 watts, 11 watts, 14 watts, and 24 watts. Compact fluorescent lamps have been finding wide application for almost all application because of their high light output to watt ratio, and also because of the attractive light color. CFL lamps, therefore, should be widely used for energy-saving purposes. However, for reading areas, library areas, educational buildings, laboratories, fluorescent lights give better service and thus should be selected for these purposes. It is worthwhile mentioning that fluorescent lamps with high-quality ballast closely meet the energy-saving purpose. In item 4 of section 1.2.8, we have LED lights. LED stands for light-emitting diodes. These types of lamps are the most energy-efficient type of lamp. Light is produced when an electrical current passes through a microchip, which then illuminates these small diodes. They are typically 3 to 5 diodes in the type of lamp shown on this slide. As you can see, this looks like an incandescent bulb. However, it has the electronics built into the assembly, and you can actually install it right into a base that would accept incandescent bulbs as well. Compact light fitting formed using a cluster of LED is currently used to replace a conventional lamp. An LED operates at very small voltage. These are good for lighting, energy efficient, and almost have negligible heat dissipation. These are good for relaxed environmental interior lighting as well. LED lights are becoming more and more popular because of much lower power consumption compared to the other lamps. Item 5 of section 1.2.8, halogen lamp. These types of lamps work similar to incandescent lamps. The filament is comprised of tungsten, which is sealed in a bulb with an inert gas and a small quantity of halogen, typically iodine or bromine. When an electric current is passed through the tungsten, it reacts with the halogen via a chemical reaction and produces the light. Halogen lamps are used for spotlights, decorative lights in shops, commercial spaces, inside showcases, stage lighting, and project lights. Due to high rise and UV lighting output, these should be avoided for interior lighting unless needed. Item 6 in section 1.2.8, the Mercury vapor lamp. This type of lamp is similar to a fluorescent lamp in that an electric arc is passed through vaporized mercury to produce light. The bulbs can be clear or coated with a phosphor. These have been widely used for shops, streets, for high bay lighting, warehouse lighting, and similar special lighting. Most likely, this type of lamp will be discontinued within the next 5 to 6 years due to some in its ill effects. Metal halide lamp is coming up as a better alternative to make mercury vapor lamps attractive and available for many applications. Metal halide lamp indicated in item 7 of section 1.2.8. These types of lamps produce an electrical arc between two electrodes in an atmosphere of argon, mercury, and metal halides, which are produced by combining halogen with a metal. These are available in a number of watt ratings. For example, 150 watt, 200 watt, 250 watt, 500 watt, 1000 watts, and 2000 watts. These lamps are good for exterior lighting, indoor and outdoor athletic facilities, for high bay lighting, warehouse lighting. These are required where massive flood lighting is required from high altitudes for covering large area. This is more of a clear white light when compared to other lamps that we've discussed thus far. Section 1.2.8, item number 8, high pressure sodium lamp. In these type of lamps, sodium is pressurized under high pressure with an arc tube with xenon and mercury. An electrical current is then passed through the arc tube. A ballast is utilized to control the current through the lamp. This produces a golden to white light. These are available in a number of watt ratings, such as 40 watt, 50 watt, 70 watt, 100 watt, 150 watt, 250 watt, and 1000 watts. These are good for exterior lighting, lighting for areas where higher concentration of vehicles and people exist, such as street lighting, building exteriors, and security lighting as well. Item 9 of section 1.2.8, the low pressure sodium lamp. Similar to high pressure sodium lamps, except that the sodium and gas within the arc is at a lower pressure. However, because of their poor color rendering, typically yellow to orange light, they are somewhat restricted in application. For outdoor lighting, such as street lights and security lighting, where faithful color rendition is considered unimportant, this type of lamp may be used for street lighting, observatory, parking lot, and similar types of areas. Item 10 in section 1.2.8, the solar PV cell-powered LED lights. This type of lamp is a photovoltaic cell that generates electricity by absorbing sunlight and then using that light energy to create electrical current. The current is typically stored in a battery until it is needed. These lamps are typically operated with a photocell that will allow the stored energy in the battery to be released and provide light once daylight conditions are low. These fittings require solar panel, solar battery system apart from the cluster of LED. For outdoor lighting, such as street lights, security lights, outdoor parking, this type of light fitting may be used. Section 1.3.1, electrical symbols used for electrical drawings. A list of general graphic symbols used for electrical drawings is given in Table 8.1.15. These are given as guidelines. In case of justified reasons, a designer may modify certain symbols. The table is titled Symbols Used for Electrical Drawings. In the first column gives us a serial number. This is a portion of the table. The code user is going to look at this particular section for all of the symbols that are indicated in the code. We have a few examples here, such as serial number 1, the main distribution board, MDB, and the associated symbol in the last column. As we move down, we have the floor distribution board. As you can see, it's a totally different symbol that indicates the floor distribution board. The distribution board, sub-distribution board, and then we get into the ceiling fan symbol. As you can see on the right-hand side, it's a circle with lines and a dot in the middle. The exit light pendant type light fixture is a circle with EX indicated in the middle of the circle. The wall-mounted exit light is indicated as a circle with EX and a wall mount to the left bracket indicated in the symbol. We also have socket outlets indicated here. The 2-pin socket outlet, single phase, is described as an arc with 2 lines projecting perpendicular to a vertical line. We also have a 3-pin 13-amp switched outlet single phase. It looks similar to the 2-pin outlet. However, it has 3 projections perpendicular to the vertical line, such that we can tell by looking at an electrical drawing that this is a 3-pin 13-amp switch socket outlet. Additionally, we have weatherproof and weatherproof socket outlets with the WP indication on the symbol. A single pole, single throw switch is indicated 2 ways. We have a diagram of an open switch with 2 connection points in the middle of the table, and in the symbol column we have another symbol that we could use for a single pole switch. The same thing with the double pole or 2-pole switch indicates the same type of symbols. And again, the code user will go to section 1.3.1 and locate this table for many other symbols that may be indicated on electrical drawings. Section 1.3.2 covers estimating the load of a building or complex. Estimating the load of a building has to be started with the list of the connected loads in a building. This estimation is accomplished by listing all the loads in a building, starting with each individual room. These individual loads will be combined to obtain the total load for the building. It is important that all loads are included. This includes any lifts, water pumps, ventilation systems, and any other installed equipment, applying appropriate diversity factor to the calculated load. Maximum demand and diversity is covered in section 1.3.2.1. 2 items need to be determined, which are 1, maximum demand, and 2, diversity factor. These are needed in completing the load calculation and in the computation of current. In determining the maximum demand of an installation or parts thereof, diversity shall be taken into account. Appendix A gives some information on the determination of the maximum demand of an installation and includes the current demand to assumed for commonly used equipment together with guidance on the application of allowances for diversity. Let's take a look at Appendix A. Table 8.A.1, titled Allowances for Diversity, is indicated in this slide. However, before we go into the table and study the table, some information on the determination of the maximum demand for an electrical installation is provided in this appendix. It also includes some notes on the application of allowances for diversity. It is impossible, however, to specify the appropriate allowances for diversity for every type of installation, since determination of such allowances call for special knowledge and experience. The figures shown in Table 8.A.1 are therefore intended to act as a guideline. The current demand of a final circuit is determined by summing the current demands of all points of utilization and equipment in the circuit. We will now look at the table. The first column of the table indicates the proposed of final circuit fed from conductors or switchgear to which diversity applies. 4 distinct items are given to us here: lighting, cooking appliances, motors other than lift motors, which are subject to special consideration, and water heater, thermostatically controlled. The first column provides typical household installations, including dwellings of a block. These are the types of premises that were given in this case. 66% of the total current demand. We have 10 amperes at 30% FL of connected cooking appliances in excess of 10 amperes plus 5 amperes if socket outlet is incorporated in the unit. This provides us with a method to calculate the demand current based upon our estimation of the total load. We also have types of premises such as small shops, stores, offices, and business premises, and small hotels, boarding houses, and guest houses, etc. With respect to each type of premises, we may be provided with allowances for diversity. Let's go through a few examples regarding this table. What is the demand load for a total lighting current demand load of 16 amps in an individual household? First step, let's use and locate the applicable allowance for diversity in Table 8.A.1. The lighting we find in Item 1. We move to the right-hand side for the type of premises, and we obtain the value of 66% total current demand for lighting load. The next step is to apply the factor of 66% obtained from the table to the current demand load. We simply write the equation according to the decimal equivalent of 66%, 0.66, and we multiply it times 16 amperes, which equates to 10.6 amps. Next example, what is the demand load for appliances in a small bakery with 2 ranges, 40 amperes each, a mixer, 20 amperes, and a bread slicer at 10 amperes. First step, let's locate the applicable allowance for diversity in Table 8.A.1. In the premises, we have small shops, stores, and offices, as well as business premises. The first column, we need to go to item number 2, cooking appliances. We have the values indicated as 100% full load of largest appliance plus 80% full load of the second largest appliance plus 60% full load of remaining appliances. We will apply this in the next slide. Our next step is to take the appliances and rank them in the order from largest current to smallest. In this case, we have 2 appliances at 40 amperes each. We have the other appliance at 20 amperes and our last appliance indicated at 5 amperes. We can now apply the allowances for diversity in order as indicated in the table. We take our first appliance that has the highest or the largest current, 40 amps times 1.00, that is 100%, plus 40 amps times 0.80, plus 20 amps times 0.60, plus 5 amps times 0.60 equates to 87 amps would be our amp for demand. In another example, what is the demand load for a thermostatically controlled water heater with a current of 15 amps that is located in an office? Our first step, as with the previous examples, is to look at Table 8.A.1 for the allowance for diversity. Here in the table, we go down the first column to item number 4, water heater thermostatically controlled, and we move over to the type of premises, which is small shops, stores, offices, and business premises. We find that no allowance for diversity is permitted, so the demand load must remain at 15 amperes for this thermostatically controlled water heater. Table 8.A.2, titled Current Demand to be Assumed for Points of Utilization and Current Using Equipment, is also given in Appendix A. The current demand of a circuit supplying a number of final circuits may be assessed by applying the allowances for diversity given in this table to the total current demand of all the equipment supplied by that circuit. In the table, the allowances are appraised either as percentages of the current demand or, where followed by the letters FL, full load, as percentages of the rated full load current of the current using equipment. After the design currents for all the currents have been determined, enabling the conductor sizes to be chosen, it is necessary to check that the limitation on voltage drop is met. We have the table indicating the point of utilization or current using equipment. As you can see, we have 15 amp sockets, 13 amp socket outlets, 5 amp socket outlets. Our current demand to be assumed with each one of these is indicated in the right-hand column. So for a 15 amp socket outlet, the current demand to be assumed is 15 amp with diversity applied. 13 amp socket outlets, we have 13 amps with diversity applied. And the 5 amp socket outlets must be at least 0.5 amp. We have other utilization and equipment, such as protected outlets other than the above mentioned socket outlets. We must provide the current demand to be assumed at the rated current of these socket outlets. Our lighting outlet is the next point of utilization, and the current demand for lighting outlet is the current equivalent to the connected load with a minimum of 100 watt per lamp holder. Any household cooking appliances, we say that the first 10 amp of the rated current plus 30% of the remainder of the rated current plus 5 amps if a socket outlet is incorporated in the control unit. Finally, the last item for point of utilization is all other stationary equipment and appliances. The current demand for this particular point of utilization equipment is the standard rated current or nominal current must be applied for the current demand to be assumed. Section 1.3.2.3, Estimation of Electrical Load in Watts. Energy efficient and energy saving could be and should be considered in estimating the electrical load. The watt rating of individual equipment fittings connected to the system need to be listed and added. Typical watt ratings of some of the equipment fittings are shown in Table 8.1.16, which may be used for estimation if the actual values are not known or specified. During the design of electrical systems for buildings, specific information regarding appliance may not be known. Therefore, Table 8.1.16 provides estimated ranges for these loads as guidance for design. As mentioned in the previous slide, this table provides estimated loads for various fittings and fixtures. The various fitting and fixtures are provided on the left side of the column, and on the right side of the column, the ratings in watts is given. As an example, we can pick a type of fitting or a fixture, such as compact fluorescent lamp, that has ratings in watts ranging from 5 to 65 watts. If we move further down the table, for ceiling fans, we have ratings in wattage of 100 watt max. Pedestal fans will give us 120 watts maximum. Exhaust fans, 100. When we move to the right-hand portion of the table, the items listed in the right hand of the table, such as microwave oven for domestic, has a range of 1200 watts to 1500 watts that we could use for estimation purposes. Computer without printer, 200 watts. A computer with a printer will give us anywhere from 700 watts to 800 watts accordingly. If we have a window type AC machine that is 12,000 BTUs per hour, we have a wattage of 1,500 watts as an estimate. Calculation of current is covered in section 1.3.2.4. For the calculation of current for the selection of cables and breakers of fluorescent lamps, the ratings are to be multiplied by a factor of 1.65 to take care of the power factor and the starting current situation. For the calculation of current of the ceiling fans, table fans, pedestal fans, exhaust fans, again, the rating are to be multiplied by a factor of 1.65 to take care of the power factor and starting current situation as well. Lastly, small inductive loads up to 1 kilowatt. We need to understand that the calculation of current must also be multiplied by a factor of 1.65 to take care of the power factor and starting current situation. The factor shall be higher for higher rated motors above the 1.0 kilowatt. As an example, determine the rating in watts for cable serving a lighting system in a large storage room. There are 20 to 1,200 millimeter long fluorescent lamps in the space. Our first step is, let's use the estimated load from table 8.1.16 for fluorescent lamps. In table 8.1.16, we follow down to the nominal length of 1,200 millimeter fluorescent fixtures. We come up with the ratings in wattage of 40 watts. Our next step is to use the value selected from the previous table and multiply by the number of lamps. There are 20 lamps in our example. We multiply that times 40 watts per lamp, and this equates to 800 watts. In our last step, we need to apply the factor of 1.65 required from section 1.3.2.4, and we calculate the total wattage of 1,320 watts for that particular lighting application. Minimum load densities are given in section 1.3.2.5. While estimating the electrical load, the minimum load densities to be considered are those shown in table 8.1.17. This table gives us the type of occupancy and the unit load in watts per meter squared. We have two columns, non-AC and AC columns. The table provides the loads for us to calculate based on the area according to the type of occupancy. As we can see as an example, if we take an example such as a hospital, non-AC equates to 32 watts per square meter of space for non-AC. If we include the AC, we are up to 80 watts per meter squared for that particular occupancy. As an example, let's determine the minimum load for a 100 square meter single-family dwelling with air conditioning. Our first step is let's use the load density from table 8.1.17, an air-conditioned single-family dwelling. The load that we have is picked from the table. The type of occupancy is a dwelling single-family. We go over to the last column and get a value of 75 watts per meter squared. The last stop is we multiply the unit load by the area of the building. 100 square meters times 75 watts per square meter equates to 7,500 watts that we must use to calculate. Socket outlets and plugs are contained in section 1.3.3.2. The requirements of this section give us that the number of socket outlets in a building depends on the specific requirements of occupants and the type of building. Adequate number of 13 amp switched flat pin shutter socket outlets shall be provided and arranged around the building to cater to the actual requirements of the occupancy. 15 amp round pin socket outlets shall be provided for specialty air conditioners and water heaters of such ratings only. Continuing with section 1.3.3.2, for residential buildings, the minimal guidelines given in Table 8.1.18 shall be used to determine the required number of 13 amp switched flat pin shuttered socket outlets when actual requirements cannot be ascertained. All socket outlets shall conform to BDS 115. Viewing Table 8.1.18 below, titled Minimum Number of 13 amp Flat Pin Socket Outlets, we look in the residential type of an occupancy. The location is given below: bedroom, living room, drawing room, dining room, toaster, kitchen, bathroom, veranda, refrigerator, air conditioner. On the right-hand side of the table, the number of switch socket outlets is provided based upon the specific location in the residential building. As an example, in a bedroom, we must have a minimum of 2 switch socket outlets. A drawing room would require 3, a dining room 1, a kitchen 1. There are no switch outlets permitted within the bathroom. Refrigerator 1, veranda 1, and if we have an air conditioner, 1 for each room. This gives us a good guideline to design the minimum number of switch outlets, or we can design more depending upon the function of the room as well. Section 1.3.3.3 describes ceiling rows. A ceiling rose is needed for terminating the point wiring for a light or a fan in the ceiling. A ceiling rose shall not be installed in any circuit operating at a voltage normally exceeding 250 volts. Normally, a single pennant shall be suspended only from one ceiling rose using a flexible cord. A ceiling rose shall not be used for the attachment of more than one outgoing flexible cord unless it is specially designed for multiple pennants. Item C. A ceiling rose shall not contain a fuse terminal as an integral part of it. The ceiling rose shall conform to BS 67. Finally, E. Luminaire supporting couplers are designed specifically for the mechanical support as well as for the electrical connection of luminaires and shall not be used for the connection of any other equipment. To the right-hand side, we see a picture of a ceiling rose. We use this to loop conductors from one ceiling rose to another, and we can take the switch wires from the ceiling rose down to the switchboard and back up to the ceiling rose to work as a junction port for the illumination switching of the light that is fed by the ceiling rose. Section 1.3.15, designed for electrical wiring. Design of electrical wiring must be done following the provisions provided in this chapter. Detailed design drawings must be prepared by an eligible engineer for complete execution of the electrical works mentioned in this document, and any other new items arising because of the evolution of new technologies in the near future. Typically, there must be conduit layout drawings indicating the conduit layouts, the locations of the switchboards, locations of the sockets, locations of the BDBs, SBDBs, location of the DBs, etc. A distribution diagram of all of our distribution boards as applicable, indicating the ampere rating of the incoming main circuit boards, the molded case circuit breakers, interlinking cable sizes, and the ECCs must be presented as well. Detailed circuit diagrams of the circuits and the distribution boards, as applicable, must be presented as well. Detailed drawings of earthing and earth inspection pits and any other complicated parts must be presented also. The contractor shall prepare as-built drawings after completing a project. Note, the code user must also reference Section 1.3.3.2, socket outlets and plugs, for specific requirements regarding socket outlets and plugs to understand how to design the circuits, specify, and install them in various areas of residential and commercial buildings. In Section 1.3.3.2, in general, all socket outlets must be switched, combined, and shuttered. Item A, general requirements of socket outlets. Socket outlets shall be 13 amp, switch shuttered, 3-pin, flat pin type. All socket outlets must be switched and shuttered and shall be for 3-pin, flat pin type, 13 amp plugs fitted with tubular fuse. The corresponding plugs must be fitted with fuse. The maximum fuse rating shall be 13 amp for 13 amp sockets. The fuse rating may be smaller depending upon the current rating of the appliances used. An example shows the 3 flat pin outlet and the shutters indicated on the left-hand side. We also have at the top the outlet switch to turn the power on and off with respect to the socket outlet. The plug is a 3 flat pin plug, a rectangular type as shown on the right-hand side. As indicated, socket outlets and plugs continued. The phase wire, which is the brown cable, shall be connected to the L terminal of the socket outlet through the combined switch, and the neutral wire, colored blue, shall be directly connected to the N terminal of the socket. The earth continuity conductor, ECC, yellow plus green bicolor cable, for such a socket shall be connected to the earth terminal of the socket. Plug wiring example is indicated below, where we have the cable or the cord grip and the indication of the terminals. N is our blue or neutral wire. E is our earth continuity conductor, which is the ECC, that is colored yellow plus a green bicolor cable. And the L terminal is our brown or our live wire being attached to the L terminal. Round pin socket outlets of 15 amp, 20 amp rating may be used for air conditioner outlets. and water heater outlets under special circumstances. For air conditioner outlets requiring 15 amp or 20 amp rated outlets for round pin plugs may be used along with a circuit breaker or fuse protection in a box adjacent to the sockets. As with 13 amp plugs for 15 and 20 amp socket outlets shall be fitted with adequately sized fuses. 3-pin socket outlets shall be mounted on a wall 250 millimeters above the floor. Socket outlets shall not be placed in wet locations, including bathrooms and toilet rooms alike. For 13 amp and 15 amp 20 amp sockets, the earth continuity conductor ECC shall not be smaller than 1.5 millimeters squared PVC insulated annealed copper cable. The color of the ECC cable shall be yellow plus a green bicolor. Note that the ECC is to be PVC insulated. A bare uninsulated wire would not be compliant with the code. Let's understand the design requirements with respect to section 1.3.15.1, titled Design for Electrical Wiring in Bedrooms and Drawing Rooms. The location of a switchboard must be near the entrance door of a bedroom, like any other room. The location of the wall-mounted light fittings must be chosen based on the possible locations of furniture, which is also needed in other rooms. Sufficient number of 3-pin 13 amp switched shuttered flat pin sockets must be provided in a bedroom. The same principles are applicable for a living room. This section gives us specific requirements regarding bedrooms, drawing rooms, and living rooms. As we can see, we have a drawing of a bedroom below. The designer would need to place receptacles and lighting accordingly in the bedroom for the function of people that utilize the bedroom. We will look at a further design analysis on the next slide. The design must be made in such a way that sufficient clearance or space is left inside the concealed conduits when we run these circuits to the bedroom, drawing rooms, and living rooms. For the ease of pulling the cables and also for adding few more cables in case of necessity during future modification. For bedrooms and drawing rooms, the light plus fan subcircuits shall not be of more than 5 amp rating. Generally, the single core PVC insulated copper cables shall be used in concealed wiring technique or other methods. As we can see, we have a bedroom that has been laid out with a light switch at the room entry door. The switch controls 2 ceiling lights as designed for this room. Additionally, we have 3-pin 13 amp switch shuttered flat pin sockets located around the room as indicated around the room. There is a bed indicated between 2 windows, and we have our switched flat pin sockets on either side of the bed for utilization equipment such as clocks and other various things that may be plugged into the sockets. Designed for electrical wiring in a kitchen is in section 1.3.15.2. The sensitive item in a kitchen is placing 3-pin 13 amp switch shuttered flat pin sockets on a wall of the kitchen side table near the wall. Good distance must be maintained between the kitchen water tap and the socket. The socket for the refrigerator, if any, shall also be a 3-pin 13 amp switch shuttered flat pin socket and may be placed at the same level as the other socket. For the ease of operation, a 3-pin 13 amp switch shuttered pin socket for this purpose may be placed at the bottom level height of a switchboard, provided this is acceptable in terms of aesthetics. For kitchens, the light plus fan subcircuits shall be of not more than 5 amp rating. The example below shows a kitchen design. We have 3 ceiling lights. We have a switch that provides on and off control of 3 ceiling lights within the kitchen. We also have 3-pin 13 amp switched shutter flat pin sockets located around the kitchen. And we also have the water tap identified on this drawing, and we keep the 3-pin 13 amp socket far enough away from the water tap for safety. Section 1.3.15.3 provides requirements for switches for toilets and bathrooms. Switches for toilet lights and toilet ventilating fans must be placed outside the toilets adjacent to the entrance door, but must not be placed inside the toilet. The same rule should be followed for bathrooms. Using ceiling-mounted cord switch at the entrance path of the door of a toilet is a good idea for small toilets attached to bedrooms. Ceiling-mounted cord switches may be used with cords suspended from ceiling near the opening of the door. Below is a bathroom indicated as a drawing. We have a switch provided outside of the bathroom door that provides control of the bathroom ceiling fan light assembly. Designed for electric wiring in office rooms is covered in section 1.3.15.4. The location of a switchboard must be near the entrance door of an office room. The location of the light fittings must be chosen based on the possible locations of work table, furniture, etc. Sufficient number of 3-pin 13 amp switch shuttered flat pin sockets must be provided in each office room. In this regard, special consideration needs to be given on the possible location of computers and other office equipment. Sufficient conduits and cables must be left for future modification, as often rearrangement of cables needs to be made. For offices, the subcircuits shall not be of more than 5 amp rating. Below is a office space for 2 offices. As designed, we have the switches near the entrance door of the office rooms. The switch controls a ceiling light in each of the offices indicated as Office 1 and Office 2 below. The different arrangement of the 3-pin 13 amp switch shutter flat pin sockets in the offices have been placed there according to furniture and table arrangements in these specific offices. The engineer needs to coordinate with the architect regarding any furniture and furnishings provided in offices within our buildings to better place the lighting and the sockets around the different offices. Section 1.3.42.3, checking the conformity with the Bangladesh standard. The individual equipment and materials from part of the installation shall generally conform to the relevant Bangladesh standard, BDS, wherever applicable. If there is no relevant Bangladesh standard specification for any item, these shall be approved by the appropriate authority. Section 1.3.42.3, Item 1, inspection of the color identification of cables of wiring. For single phase, brown for live, blue for neutral, green plus yellow bicolor for ECC. For three phase, brown for L1, black for L2, gray for L3, blue for neutral, and green plus yellow bicolor for ECC and earth lead wire. Below we see an example again of our socket. Single phase socket. We have the blue neutral wire is connected to the N terminal of the socket. The green and yellow wire for our ECC is connected to the earthing outlet terminal. And our brown wire is our live wire connected to the L terminal within the socket for proper wiring. This is a color coding, so everybody can identify with the IEC standard now for new wiring. Item 2, inspection of earthing terminal, earthing bus. Inspection should be made to check whether brass-made earthing terminals have been provided inside the metal back boxes of the switches and socket boards, and whether the ECCs of the sub-circuit have been terminated in these terminals. Inspection should be made to check whether at least one copper earthing bus bar has been provided in the BDBs, SDBs, FDBs, DBs, MDBs, and the LT panel, and whether ECCs have been appropriately terminated in these bus bars using hexagonal head brass bolt and nuts. Also, it should be checked whether the earth lead wires have been properly terminated in the LT panel, MDB, DB, as appropriate. Insulation tests are given in item 3. The insulation test is one of the most important tests for electrical installations in a building. Insulation resistant tests shall be made on all electrical equipment using a self-contained instrument such as a direct indicating ohmmeter of the generator type. DC potential shall be used in these tests and shall be as follows, or an appropriate measure. Circuits below 230 volts to 500 volts measure. Circuits between 230 volts to 400 volts, 1000 volt measure. The minimum acceptable insulation resistance value is 5 mega ohms for LT lines. The minimum acceptable insulation resistance value is 5 mega ohms for LT lines. Before making connections at the ends of each cable run, the insulation resistance measurement test of each cable shall be made. Each conductor of a multi-core cable shall be tested individually to all other conductors of the group, and also to Earth. If insulation-resistant test readings are found to be less than specified minimum in any conductor, the entire cable shall be replaced. All transformers, switchgears, etc., shall be subject to an insulation resistance measurement test to ground after installation, but before any wire is connected. Insulation tests shall be made between open contacts of a circuit breaker, switches, etc., and between each phase and earth. As seen in the graphic below, we have a megger that is actually inducing a voltage through the conductor and tied on to a metal pipe. This test is testing for any leakage coming through the insulation from the conductor. Inspection of the installation is required and given to us here in section 1.3.42.3, item 5. On completion of wiring, a general inspection shall be carried out by competent personnel in order to verify that the provisions of this code and that of the Electricity Act of Bangladesh have been complied with. A certificate may be issued on satisfactory completion of the work in a format as shown in Appendix C. Items to be inspected are detailed in the following sections. We will now take a look at Appendix C and the certificate required by this section. In Appendix C, we have the completion certificate form regarding electrical works. It indicates that this is a certification that the installation detailed below has been installed by the person responsible for installing the work, and indicates several lines that need to be filled out. The electrical installation at a particular location is required. The voltage and system of supply information is required. The particulars of works indicated in item A, internal electrical installation, requires the number, total load, type or system of wiring for lighting points, fan points, socket points of differing sockets, such as 2-pin 5-amp sockets, 3-pin 13-amp flat pin sockets, and 3-pin 15-amp round pin sockets. Item B, the applicant must provide the description, horsepower or kilowatt, and type of starting of various motors. Item C, if the work involves installations of overhead line and or underground cable, then information such as the type and description of the overhead line is required, the total length and number of spans is required, and number of street lights and its description. The form is continued on the following slide. Continuing the completion certificate form, item 2, total length and size of underground cable, number of joints, end joint, T-joint, straight through joint, requires a numerical value for the number of these joints in every case. Item D, earthing, description of earthing electrode, number of earthing electrodes, type and short description of brass earthing clamp, number of brass bolt nuts provided in the brass earthing clamp for the termination of earth lead cables, the size of each of the main earth lead cables, and number of main earth lead cables provided. Test results is the next category. Item A, insulation resistance values. A1, insulation resistance of the whole system of conductors to earth in megaohms. Next, insulation resistance between the phase conductor and neutral. This is item number 2. Item number 3 is for polyphase systems. The insulation resistance between the phase conductors in case of polyphase supply. As you will see here, the old existing color code is indicated with respect to the colors of phases. This is the old existing IEE standard. A note to the code user with respect to the completion form here, any new installations would need to be changed to the new color code indicated in the IEC standard. Next is item B, polarity test. Polarity of non-linked single-pole branch circuits, and C, earth continuity test. A continuation will follow on the next slide. Continuing the completion certificate form, maximum resistance between any point in the earth continuity conductor, including metal conduits and main earthing lead in ohms. Item D, earth electrode resistance. Resistance of each earth electrode must be indicated in ohms in each case, depending how many electrodes are installed and being tested. Item E, lightning protective system. Resistance of the whole of the lightning protection system to earth before any bonding is effected with the earth electrode and metal in on the structure in ohms. Last, the signature of the supervisor is required, name and address below, and the signature of contractor is required, name and address below. This would complete the certificate form for the electrical works. This is the end of the presentation. Thank you for your participation.